All right, thank you, Michael, for that wonderful introduction. Today I'll be presenting my thesis work on autonomous exploration of unknown environments. And this thesis has largely been constructed in connection with and inspired by several real-world exploration missions. And the three that you're seeing up here are the DARPA Subterranean Challenge, aircraft envelope expansion with the Air Force Test Pilot School, and then the last one here is the Viper mission to the lunar South Pole. So we'll see later on how the contributions of this thesis connect back to these real-world applications. But first, I think it's helpful to sort of zoom out, look at the high-level picture, and get a sense of what is autonomous exploration and why is it important. And I think the best way to do that is with an example. So if we consider a rover here exploring the surface of another planet, we can say that the rover probably has a good understanding of the area immediately surrounding it. But the area that lies in front of the rover beyond is where we have a lot of uncertainty. So the rover here is working with a small drone, and that drone can fly in front of the rover and take these measurements of what lies beyond. And so the question here is, what is the best sequence of actions for this drone to take, given some limited amount of energy budget, to reduce the uncertainty in the area that lies in front of the rover? So that's an example of autonomously exploring an unknown environment. A similar example, a little closer to Earth, is in this disaster response scenario, where we want to send in this autonomous submersible robot to map the extent and severity of this oil spill so that we can better focus our recovery efforts. Both of those examples involved an agent autonomously exploring either a two-dimensional or three-dimensional physical environment. But autonomous exploration is not just limited to these 2D and 3D environments. We can explore higher dimensional spaces. And a good example of this is in aircraft system identification and envelope expansion, where now the exploration problem is over the aircraft model itself. So the exploration problem here still involves taking these sequence of actions into the future, but now we're trying to reduce our uncertainty in the actual model of the aircraft. And then lastly, just to drive this point home with one final example, in archaeological sample imaging or in medical imaging, oftentimes these imaging devices are using very fine raster scans of the sample. And so when you're only imaging one sample or so, this isn't really an issue. But when you have hundreds or thousands of samples to take images of, then oftentimes you can drastically reduce the time and cost taken to collect these samples using either adaptive paths for that the imaging device or quantifying your uncertainty about the actual sample that you're imaging. And so what all of these different examples here have in common are that they are all examples of the adaptive informative path planning with multimodal sensing problem. And so what this problem is that it involves an agent, and that agent has access to multiple sensors on board. So these sensors could be LiDARs, they could be spectrometers, cameras, ultrasound sensors, any type of sensor we could have. The agent with those sensors then also has some constraints that it has to obey. So these could be constraints on the amount of battery it has, fuel on board, time constraints, or dollar constraints as well. So given these sensors available to the robot, given these constraints that it has to obey, the problem is then, how does the agent plan this sequence of actions into the future to reduce its uncertainty in some underlying quantity that it's trying to estimate in the environment? That is the adaptive informative path planning with multimodal sensing. And this thesis is focused on developing new tools for efficiently planning paths to acquire information about these unknown environments. And so the layout for this talk today is going to, we already just looked at sort of a high-level overview of autonomous exploration. We're next going to go into the actual contributions of the thesis at a high level, and then we're going to look at three of them in a little bit more detail. So at the high level here, focusing on autonomous exploration, we're coming at that from two different themes. The first one that we'll talk about here is the adaptive informative path planning with multimodal sensing problem. And we'll highlight two of our contributions there. The first on sequential Bayesian optimization, and then the second on an approximate optimization method. The other theme here is on safe exploration. And so the one contribution we'll talk about there is in informative input design. And that's related to that case where we have a model of some system and we're trying to take these actions to reduce our uncertainty about that system model. And so looking at these contributions in a bit more detail, for the first contribution here on the sequential Bayesian optimization, we're developing this belief state sequential decision-making process formulation for the informative path planning problem. And then we're solving that through a few different methods that we'll talk about in detail. For the approximate optimization method, we first show that you can formulate the informative path planning problem using Gaussian processes as a mixed integer program. And then we show that we can also introduce this approximate optimization method that scales to these really large problem instances. And then lastly, for that work on informative input design, that's where we have this model of the system, and we're trying to plan these control inputs to reduce our uncertainty in that system model. So looking first at the informative path planning problem and how we're formulating this problem here. So we're representing the environment as a graph where we have n nodes in this graph. The nodes are also connected to each other with edges. And so in practice, what this graph is actually representing, right, in the rover exploration case, those nodes are representing actual physical locations that the rover could move to in the environment. Similarly, in the disaster response scenario, same idea, just maybe at different scales or resolutions here with that graph. So given this graph-based setup, we're assuming that the agent is going to be starting at some start node, and we want to reach some goal node. So the problem then boils down to, how do we plan out this sequence of actions? And here the sequence of actions is the sequence of nodes that we're visiting in this graph. So how do we plan those to maximize the amount of information we are collecting from this environment? And so those actions that we're taking, we're representing them as the sequence of nodes in this path that we want to construct. So all we're saying here is that the path is just made up of these sequence of nodes up to node L, where L is the length of the path. And we can have different constraints on this path as well. So one example of a constraint that we could have is on the energy budget here. So this could be just some budget, whether it's time, energy, or distance. And then we're saying that the nodes, the edges along our path, we want the total sum of the cost of those edges to be less than some budget that we're specifying. So that's one example. We'll talk about other examples of constraints that we could have. And then just to make the problem here a little bit more general, in some cases, we may only be interested in predicting at a subset of these environment locations. So we might not want to make predictions at every node in the environment, but just a few of them, and that's shown in these orange nodes here. So we're calling that vector that we're trying to predict x here, where x is representing those actual orange locations here in our graph. Why would we only want to predict at a subset? Well, in the case where we have an extremely large graph, and this could represent the case where we're planning over a very large space or at very fine resolutions, then typically it's one, not computationally tractable to store all of these nodes in memory and make predictions at all of these locations. And two, it often doesn't gain us that much in terms of just taking a subset to make those predictions. So that's why we introduced that sort of generalization there. So now with this path setup, how are we actually observing this quantity that we're trying to estimate? So we have this measurement model that we're showing down here, and what this is saying is the actual measurement that we're receiving is this yi measurement. And then this ai, this vector here, is what's characterizing the measurement that we receive. So at a specific node, this a vector is telling us how are we actually going to observe those orange nodes that we're interested in. So that's our measurement characterization, and then we're assuming that we have some zero mean Gaussian noise as well. So now with this setup here, with the path setup and with the observations that we're receiving, we can construct an estimate of what we think the vector x actually is going to be. So that's this x hat estimate. And if you're familiar with Gaussian processes, this is exactly the Gaussian process mean and covariance written in a slightly different form. And we'll talk more about Gaussian processes later. The key thing to keep in mind right now is that we can make this estimate, and then we can also quantify our uncertainty in that estimate. And so when we talk about non-adaptive informative path planning, that's the case where we're only using the covariance matrix sigma there in our objective. The reason it's non-adaptive is because you see that the measurements don't actually affect that covariance matrix. In the adaptive case, you're typically using both the mean and the covariance to quantify what your objective is. So we'll look at first this non-adaptive case here, where we're only considering the covariance matrix. And so from the optimal design of experiments field, there's a few different information objectives that we can state here. And so regardless of whichever of these information objectives we're using, we can just say, okay, we have some information objective here, phi of p. So that's the amount of information that we're storing in this path. And so the informative path planning problem then becomes we want to minimize this 5P objective subject to our path obeying these constraints. So that is the informative path planning problem here. And so before we look at our specific contributions here, I think it's helpful to sort of frame this in the scope of how previous approaches have looked at this problem. So I've categorized this related work into some of the most popular approaches and highlighted some of the key papers here. And all of them really stem back to the sensor selection problem, which is a very similar problem, but it's different in the fact that we're not actually considering the path constraints. So you have some environment and you're just saying, how do I place sensors in this environment to estimate some quantity of interest? So then the follow-on works here, looking at informative path planning, introduce these integer constraints into the problem so that you now have basically a path. You're considering how am I moving from point A to point B, and those path constraints are using these integer variables. Another popular approach is through these approximate methods where typically they're using Gaussian processes here to formulate the spatial correlation among the nodes in the environment as well as the information objective, and then they use either branch and bound or other heuristics to produce a path solution. And then more recently, learning-based methods have become popular where typically these are looking at training a neural network offline to learn informative actions and then querying that network in an online tree search-based setting to produce a policy. So in the context of this related work here, how the methods that we're going to be talking about today differ is that we're considering additional path and sensor type constraints in these problems. So we have multiple sensors available to us. We're going to be formulating the information objective using Gaussian processes. And then we're also going to consider both the adaptive and non-adaptive case of the problem, as well as the multimodal and multi-agent problem variants. And then lastly, we're also going to be looking at very large graphs here, where we have tens of thousands of nodes and edges, and that has previously not been looked at. So that brings us here to our first contribution on sequential Bayesian optimization. And so in this contribution, what we're looking at here is representing this sequential decision-making process using a distribution over functions. And that's what a Gaussian process is. So just a very quick background on Gaussian processes. A Gaussian process here is a distribution over functions. So what we're showing here in white is the true function value. All we've observed from this true function right now is just that one noisy observation. Because it's a distribution over functions, we can get the mean and covariance of our prediction. So we're showing in this thick blue line, that's the mean of our prediction, and then the shaded blue is the variance. And since it's a distribution over functions, we can sample from this, and the samples from that distribution are actual function values, and that's what you're seeing in those thin blue lines. So as we take additional measurements, we can update our belief here, and as we collect more and more measurements, we'll more closely match the true underlying function. And the nice part about Gaussian processes, and one of the reasons that they're popular, is because you can quantify your uncertainty in these predictions of the true underlying function. And so we use this idea here in a Markov decision process. And a Markov decision process is just a mathematical formulation for sequential decision making under uncertainty. So what that looks like here is that we're going to have some observation. We have our current Gaussian process belief, and then we're going to take some action. We'll receive some reward for this action that we take, and typically this action is going to tell us where should we sample at to collect new measurements. So we take that action, we receive some new observation, we update our Gaussian process belief, and then we can repeat this. So now we're going to take some new action, we're going to receive some reward based on how we're reducing the uncertainty in the Gaussian process, and we'll continue on sequentially like this. And so that's why it's sequential Bayesian optimization here. So that's the high-level idea, showing it with a one-dimensional example here. What we're actually interested in is applying this to Gaussian processes with multiple dimensions. So taking this idea now and using it for the informative path planning problem where we have this graph environment set up, what the belief MDP actually looks like here for the formulation, we have the following components. So we're going to have the belief state, the action, the transition, and reward. So the belief state here is made up of the following components. This P term is the current path up to time t. So this is all of the nodes that we visited up to the current time. These are the observations that we received along that path, and then also the measurement types that were used as we went through that path. This here is the amount of energy budget that we have remaining. So how much of our total budget do we have left at the current time step? And then we also have the Gaussian process mean and covariance there, and that's where we get this belief MDP setup, because we have the belief distribution in our state here. The actions that are available to us, this NG of I is just the neighboring graph nodes of the current node I, so which neighbors can we move to, and then also what sensing action are we going to take. So we have multiple sensors to choose from, which sensing action is what that U SJ is corresponding to. For the transition here, that's going to involve a belief update on the Gaussian process. So this is where we're updating our belief with the measurements that we've received. We can also include transition uncertainty here in actually how we move from one node to the other. So we might have some actuator dynamics or disturbances that would affect us from actually moving to the node that we wanted to. And then lastly, we have the belief-dependent reward here, where we're going to talk about the actual form of this reward function here on the following slides. But the key thing for now is just that it's going to depend on our actual belief state here. So this is the overall belief MDP setup. So one of the problems that we applied this to was the rover exploration problem. And in this problem, the agent, which is the rover, can choose between two sensors. It can choose to drill, where the drill is very precise, but it's also very costly. It can also choose to use the spectrometer, where the spectrometer is not as precise as the drill, but it's also not as costly. So we have this trade-off between those two sensors. And so one example of this problem is using this grid-based setup here, where we have, in this case, we have 10 different measurement types scattered throughout the environment. So each different measurement type is represented by a different color here. And so the agent receives a positive reward if it drills in a cell with a measurement type that it hasn't yet seen. So it hasn't yet drilled this measurement type. It gets a negative reward if it drills in a cell with a measurement type that it has already previously seen. So now what this belief-dependent reward here looks like is that as this agent moves throughout the environment, it's going to be drilling, and it's going to be keeping track of the history of drill samples that it's received. So when we come to a new location now, and we are trying to decide, should we drill in this location or not, we have access to that Gaussian process belief. So we're going to query that Gaussian process and say, what do I think the actual measurement value is at this specific location? We can get that mean estimate, and because it's a distribution, we can also get this confidence interval associated with it. So the belief-based reward here is going to look at and say, are any of the previous drill samples that I've collected, do any of them lie within this confidence interval? If they do, then it's a good indication that it's probably not a good idea to drill in that location, because we're going to get a negative reward for drilling there. So just keep in mind that these colors are actually representing numerical values here that we're observing. And so just writing that same thing out now mathematically, so that was just a visual description, but now if we just want to write this out formally, this is just tracking the drill samples that we've received. So these are the measurements where, for our entire path so far, where the sensor type that was used was the drill. And then we also have the variance of the Gaussian process. And so the belief-based reward here is then going to be, we get a negative reward if we took the drilling action and any of those previous drill samples were inside this confidence interval that we're representing. If we're not taking the drill action, or those don't lie within that confidence interval, then we're going to reward the agent based on how much it reduces the uncertainty in the Gaussian process. So that's sort of the objective here. We're incentivizing reducing our uncertainty, but we also don't want to be too drill happy and just place drills everywhere. So to solve this belief Markov decision process, we used a variant of Monte Carlo tree search here, where we included double progressive widening. And double progressive widening is useful in tree search-based approaches where we have continuous action spaces and continuous state spaces. So the reason it's useful is because we can run into these infinite branching in terms of the width of the tree. Since we have a continuous state space, basically the tree would just continue to grow horizontally. And so double progressive widening forces us sort of artificially to go deeper into the tree. And so we looked at applying this on various different problems here. The one that I'll highlight for time is just on the rover exploration problem. And so what this is showing here, this animation, on the left here we have the mean of the Gaussian process. On the right we have the variance. And the agent in this case is represented by that pink dot that you're seeing. And when it places a drill, it's showing up as those green dots. And if it was receiving a negative reward, it would be a red dot. In this example, there's no negative rewards received. So what you can notice here is that the agent is much more drill happy at the start. And that sort of makes sense, right? Through these tree search rollouts, it's recognizing that I haven't collected any drill samples yet, so I'm going to be rewarded for placing drills. As we go throughout the trajectory, though, it becomes more conservative with where it's placing drills because it recognizes within that confidence interval, it's likely to not be rewarded positively there. And then we also compared this to some work by Shushman Choudhury. Those approaches are the POMCP and POMCP GCB methods. And so that approach was using these particle-based beliefs. And so sort of the key takeaway here is that in these problems with spatial correlation and where that spatial correlation is important, that's where we see the benefit of using these Gaussian processes because we're capturing that spatial correlation that otherwise is not captured as well with the particle-based beliefs. The limitations of this approach really stem from the fact that we're using these rollout-based methods. So if we want to plan over these longer horizon trajectories, then that's where we sort of start to struggle with how far in this search tree can we actually go. And that's where this next contribution was sort of focused on is how can we plan over these long horizon trajectories and over these extremely large graph sizes. And so first here, we're going to show that we can actually formulate this informative path planning problem using Gaussian process objectives as a mixed integer program. Then we're going to take that mixed integer program and produce this convex relaxation, and we'll talk about why this is useful in a second. So we're working with this graph-based setup still, and now we're going to introduce this integer variable z, where z is a matrix, and all z is representing is just the edges of this graph. So we're enforcing here that z has to be either 0 or 1. So when you look at sort of index into the matrix z and you look at the zij component, all that's saying is just the edge from I to j in our graph. And we're just saying that has to be 0 or 1, meaning that edge is either on our graph or on our path or it's not on our path. And so we have various constraints that we can enforce on this z variable to construct these valid paths. But since we have time constraints of our own, I'm not going to go into all of these in detail, but largely these just come from the traveling salesman problem or the orienteering problem, and are just variants of those. And so the novelty here is not in introducing these path constraints on z. The novelty is in recognizing that we can use this binary variable z in our expression for the Gaussian process covariance matrix. And so if we take these now and we rewrite our Gaussian process covariance matrix in the following form, essentially what we're doing here is because we have that zij is going to be either 0 or 1, this is essentially just picking out the nodes of the Gaussian process that we're going to be making observations at. So we can now use this and we rewrite the informative path planning problem now using this objective. And so we've now been able to write this as a mixed integer program. And it might not be immediately obvious to you looking at this, but this would be entirely convex in those A, B, and D optimal objectives that I showed earlier if it were not for those integer constraints on z. And so what we can do now is we'll just say, okay, instead of enforcing those integer constraints, let's just relax this. So instead of z having to be 0 or 1, we now say z can be between 0 and 1. And this actually works quite well in the sensor selection problem. So when we don't have these constraints, this relaxation works really well. When we do have these path-based constraints, it does not work well for the informative path planning problem. So the solution that we get from solving this problem doesn't really give us a meaningful path here. But what it does give us is it gives us a global lower bound on the optimal solution. So we now know this is the best possible that we could ever hope to achieve by solving this convex relaxation. That's why this is useful, and it's even more useful when we introduce this approximate method, because now this lower bound tells us how well is our approximation actually doing compared to the best possible that we could ever hope to achieve. And so how the approximation works here is that we start at the starting node. That's all we have in our current path. And we're going to look at the next node over. And we say, okay, if I just had these two nodes in my path, what would my objective be? I'm going to compute that value, and I store it in that node. Then I start over, and I say, okay, now just the first node and just this next node here. those are the two nodes in my path. What's my objective value? Compute it and store it. And I just repeat this for the next node, and then for all of the nodes in my graph. And so notice what this approximation is saying is that it's essentially saying, okay, if I had, when I'm looking at this node up here, I'm saying I just have this node and this node in my path. And that's essentially saying that I could just teleport up to that location, right? So initially this approximation might seem not to be very good. But what we do here is that now, because we have an approximate reward for each of these nodes in our graph, we essentially just have the original orienteering problem where we want to maximize the amount of reward we're collecting subject to our path being less than some budget constraint. And so we can solve this relatively efficiently using dynamic programming and produce a solution. Now this initial solution on this very first pass through is not going to be very good. So we can either just take the first node from this solution, or we could take like the first 10 or so. And so we'll say that we take the first 10 or so, and we store that in our path. And now we just basically repeat the process. So we have this as our path, and now we're saying, okay, this is my current path. Looking at now that neighboring node, if I added that to my path, what would the reward be? And I'm going to repeat that now for the entire graph. And I'm reconstructing this path now. I'm going to go and resolve the orienteering problem here, and then store that as my path. And so I'm just constructing the path sort of piece by piece here. And because we're doing it in that fashion, the approximation that originally wasn't very good sort of gets better over time as we construct this path in this way. And so the nice part about this is that it actually scales pretty well to these extremely large graph sizes. And so we looked at comparing to several different approaches here. So there's quite a few shown in this plot here. So just to break this down, let's first just look at this blue line here. Only look at that blue one. And this solution here is solving the exact mixed integer program. So if we had infinite amount of time and we ran this exact mixed integer program, we would eventually get the global optimal solution. Since we don't have infinite time, we limited all of these methods to 2-minute time constraints. So they all had 2 minutes, and then after 2 minutes, the best solution found would be returned. So this is that solution found after 2 minutes for the exact mixed integer program. And you can see that for the exact mixed integer program, on most of the graph sizes, it took the full 2-minute time constraints to solve. Now our approximate method here is shown in this orange-yellow color. And you see that for these large graph sizes, we're outperforming the exact mixed integer program by quite a bit. And not only that, but we're also doing so roughly 10 to 100 times faster across these different graph sizes. We also looked at comparing this against other methods as well, such as a greedy-based method and the MCTS-based method. And we see that those perform well on the small graph sizes, but as we scale up, they don't continue to perform well. And so I mentioned earlier that convex relaxation that we can use to sort of look at how well are we actually doing relative to the best possible that we could hope to do. And so this optimality gap that we're showing on the top here, the upper bound is what we get from solving our approximate method, and the lower bound is what we get from solving the convex relaxation. So we now have an upper and lower bound on the true optimal solution, and we can look at how these are performing. So looking at the A optimal objective there on the left, we can see that for budgets greater than 10 or so, and this is on a graph size of 1,600 nodes, that we're within 5% of that lower bound. So that's pretty good, because the lower bound is not necessarily going to be the true optimal, and it's likely that the true optimal is slightly above the lower bound. So we're closer than 5% to the true optimal solution. And we see similar results for the D optimal objective as well, where for budgets greater than 10 or so, we're within 5% of that lower bound for the D optimal objective. And so just to give you a sense from some of the other papers in the literature, this paper from Amarjit Singh and Andreas Krauss, they used a branch and bound type method here to produce a path, and they provide this approximation guarantee that their path produced on a similar sized graph, so with 1,600 nodes, would be no worse than 95% suboptimal. So in practice, we're seeing that we're even closer than 5% here. So that's just a comparison with some of the other papers here. And then we can just sort of qualitatively look at some of the paths that are produced here. So the white nodes that are being shown, those are the subsampled locations here. And then this is also the multimodal variant of the problem where we're placing these more precise sensors in the environment as well. And then we also looked at extending this to handle adaptive objectives and also the multi-agent version of this problem, where this is a relatively simple multi-agent setup here where the agents are assuming full communication with each other. But just to give you a sense on the efficiency here, each action for each agent is taking roughly a fraction of a second to plan. And the entire path for all three agents across all of the actions, that took roughly 3 seconds for all of those actions across all of those agents. So we can do it pretty efficiently, and we're also able to incorporate these obstacles in the environment and other variants of the problem as well. So some of the key takeaways here are that these approximations improve scalability while still being able to sort of gauge how well are we actually doing relative to the best possible that we could hope to do. And we can also extend this to other variants of the informative path planning problem as well. And so I mentioned earlier that this work on informative path planning was not just meant to be used on these small toy problems, but was developed in support of these real-world exploration missions. And specifically, the one I'm showing here is the Viper mission to the lunar South Pole. So Viper stands for the Volatiles Investigating Polar Exploration Rover. And it's a lunar rover designed to map the distribution of water ice and other volatile compounds at the lunar South Pole. And so what this looks like here in this Nobile crater region right outside is this mission area setup. And just to give you a sense of scale here, this is roughly a 4,000 by 5,000 meter mission area. And so Sherpa, which is a team at NASA Ames, and Edward Balabin, who is the lead of Sherpa, is on the call here today. Sherpa is interested in using these decision-making under uncertainty-based tools to plan these high-level mission traverses for the rover to follow. And so what one of the main goal here is to enter into these permanently shadowed craters on the moon and then drill into the subsurface and collect these drill samples from the subsurface of these permanently shadowed regions. The reason for that is because it's believed to be that there's a higher likelihood of finding water ice or other volatile compounds that have been trapped in these lunar permanently shadowed regions. So this is an example of one of the high-level traverses that might be produced from the Sherpa planning tool. And the key thing to keep in mind here is that the drill and spectrometer are not being activated the entire time across this kilometer-level traverse. They're only active in specific regions along this traverse, and those specific regions are what we call science stations. So inside one of these science stations is where we're actually activating the drill and spectrometer. And so inside one of those science stations, that's exactly where we have this adaptive informative path planning with multimodal sensing problem. So we can construct our graph inside of one of these science stations, we can produce this solution, and then we can send that to the Viper team as an initial starting point of, hey, this is what a good initial traverse might look like for you guys to use. And so if you've been following some of the news with Viper recently, you might have heard that the future is looking a bit uncertain at the moment. But we're still hopeful that the rover can make it to the surface of the moon in one way or another, and that these methods will still be useful for future exploration missions as well. And so that brings us now to our work on informative input design. And what I think is the really cool part about this is that we've been talking about these exploration scenarios over physical environments, these 2D or 3D graph-based settings. But this graph that we've been working with here, it need not be a graph over these physical environments only. It can, the nodes of the graph really can represent any general vector that we want to estimate, whether it's over space, over time, or both. And so if we want to look at now this time series example here, where sort of this represents a vector at a certain instance in time, and as we move through this graph now, we're moving through time, the value in this is that often we have many of these time series based problems here where we want to collect some snapshot of data over time. And so one good example of this is in aircraft system identification here, where the actual vector that we're interested in estimating is the state and control of this aircraft. So here we're showing the roll, pitch, yaw, roll rate, pitch rate, yaw rate, the x, y, and z velocities, and then the angle of attack and angle of side slip. We can also include the control inputs to the aircraft there as well. And so this vector now in this graph-based setup is basically just this aircraft state and control at a single time instance. So what this problem now sort of boils down to is that for the first k time steps here, we're collecting some amount of data of the state and control of the aircraft. We're going to use this data to estimate a model of our true system here. And because we're only using a finite amount of data here, we're going to have some uncertainty in the model that is produced. So this is essentially just a system identification problem here, where we've collected some finite amount of data. Now we're using that data to estimate the model. With this model that we have some uncertainty about, we then want to plan the future series of control inputs here from time k+1 up to time t. And we want to plan these control inputs in such a way that they drive us to regions of the state space that we haven't yet observed, or that will allow us to reduce the uncertainty in our model. So these control inputs will affect the state values that we're actually observing. So what this looks like is that over those first k time steps here, we have that system identification problem. And so we're going to use this linear system model here to estimate the model. And you might be saying, okay, wait, we're using a linear model here. How well is this going to do for actual real-world nonlinear problems? And it turns out that if we can do this fast enough, as we see here in a second, that the linear model actually works quite well even for nonlinear systems. So we have our linear model set up here, and then we're basically just going to now stack the data that we've observed. So we're just reorganizing things into these matrices so that we can set up this linear regression system identification problem. So what we're interested in estimating here is these A and B matrices. Those are the model parameters for our linear system. And all that comes down to is just solving this basic linear regression problem after we reorganize this. Because we're solving this linear regression problem, we can get the associated covariance of our model parameters here. So that's sort of what we're interested in using as this gauge for how well is our path performing. So we can then set this up as solving the following optimization problem, where we want to minimize some measure of our uncertainty now. And we have various constraints. The first line here is just saying that we want the previous data we've already collected, we want that to stay the same. And then we want our state in the future to follow this estimated linear model that we've constructed. And we can also have constraints on the control inputs as well as the state outputs. And to actually solve this, because the trace of gamma here that we're showing is not a convex problem, we can introduce a convex approximation. And that's how we actually go about solving this very efficiently. So what this looks like applied to one example here is, this is in the Aerobench flight simulator. And so Aerobench is a flight dynamics simulator, and here we're looking at the F-16. And so we can collect some limited amount of data here for the F-16 of both the state and controls. And then what we want to do is we want to use this to plan future control inputs to drive the F-16 to regions of the state space or different input frequencies that we haven't yet observed. And so how this performs in practice, our methods here are the two shown on the left. And then we also compared to this orthogonal multi-side method from Eugene Morelli. And that's essentially just looking at, I want to wiggle the control inputs in such a way that they're orthogonal to one another, but doing that without any knowledge of the previously collected data or the model of the system itself. And then the other method here is just a random input-based method. And so we're seeing that our methods over here, they're performing better in terms of reducing the uncertainty in that actual model that we're interested in estimating. And they're performing similarly in terms of the solution quality, the solution time as well. And so the key thing to keep in mind in this example is that this is just a one-shot planning here. Where we see the real value in this is where we do this sequentially. So we do it iteratively here. And that's exactly what we looked at here in this X-plane example. So X-plane is a realistic flight simulator. And we looked at applying our method here in real time to this Cessna 172 aircraft. And so keep in mind here that our model has no knowledge. This is a Cessna 172 to start with. We have the human fly the aircraft for the first 50 seconds and collect data as we fly. And then we give control over to our method here. And we basically just enforce some constraints. Okay, we want you to stay within this region of the flight envelope. Go for it and do whatever you want within that flight region. And so we're planning these control inputs for the elevator, aileron, rudder, and throttle. and then we're going and actually executing those, collecting the data, updating our model estimate, and then replanning online. And so we're doing this iteratively, and that allows us to continuously reduce our uncertainty in this model as we are collecting this new data and updating our model as we go. And so what the results here look like for this example, we're showing the human collected data is in that orange-yellow color, and then where our method took over is in blue here. And so that's both the state and control evolutions that you're seeing there, and this is showing sort of a gauge of the uncertainty in the true model as we go. And so both of these examples here that we looked at were for medium-sized state space problems, right, where we have 15 to 20 dimensions in our state. But what's pretty cool is that we can apply this to states, to systems with very high-dimensional state spaces. So this is now looking at systems with roughly on the order of 50,000 dimensions here. The control for this cylinder example is the rotation rate of the cylinder. And for the rod, it's the actual movement of that rod back and forth. So you might be saying, well, how can we do this for a system with 50,000 dimensions if we can't really construct a 50,000 by 50,000 matrix, and we'd have no hope of inverting that matrix? So how we go about this is that we, just like before, we're taking this time series snapshot of this system as it evolves through time. And we're using that time series data now. This is the sort of the data collection part. So we take that time series data, and then we're going to perform what's called dynamic mode decomposition on this data. So this is essentially just looking at the singular value decomposition of this time series data, and we're extracting the most prominent modes of the dynamics from that time series data. So this allows us to reduce the order of the system from roughly 50,000 dimensions to on the order of 50. And so basically we're just running this model reduction step to start with on that time series data that we've collected, and then everything else can proceed as before. So now we're just planning in this reduced model order space, and so we're solving similar optimization problem here, just now in that reduced space. We can take the control inputs that we plan, we can feed that back to the system to then re-execute, and then update our model, go to the dynamic mode decomposition step, replan, and continue on as before. And so zooming out here now on this informative input design work, we were looking at this system identification problem where we're trying to plan these control inputs into the future to reduce our uncertainty in the underlying system. We looked at these medium-sized state space problems as well as how to scale this to larger problems as well. And now zooming out sort of back to the thesis as a whole here. So we were focused on autonomous exploration of these unknown environments. And we came at that from sort of two different themes with adaptive informative path planning. And we looked at our approach through sequential Bayesian optimization as well as our approximate approach there as well. And then on the area of safe exploration with this informative input design work. Some of the future work here would involve incorporating other sources of uncertainty. So where we have uncertainty, localization uncertainty in terms of the agent not being certain about where exactly it is in the environment, as well as how its actions will actually affect the budget. So we might have uncertainty in the actual state of charge of the rover, for example. Additionally, we could extend this to more difficult multi-agent settings where we have either limited communications between the agents or adversarial agents in the problem as well. And then also planning over even longer horizon trajectories where we have to worry about some of the scalability issues there. And an area that I think is really interesting is, as a future work, would be this human agent exploration problem where you have a human exploring the environment, working with a supporting autonomous system that's trying to infer the actions of the human and take the actions itself to support the human in its exploration. I think that's a very promising area of future work. So here are some of the references for the projects that I've discussed today, as well as some of the others that I've been involved in during my PhD. So with that, I will wrap it up. Thank you all so much for listening, and I'm happy to take any questions now.